you do with your will with your slides, and I've got them called up here. Like I say, she'll probably get the check over. I think it'll do right here, perhaps. There we go.
Thank you for the professor. I'm named Shawa. So I'm the this PhD student here, and this is my research doctorate with my advisor, Dr. Autoregression, and the topic is changing point detection with Quantile Autoregression model. Yeah, this is like outline. First, do some introduction. Also, I will do some background. I will show you some my preliminary work, also technical work and reference. So first, what are change points? So change point, we can think about it little. It's like something and change the settlement, right? So change point will be defined in the different technology, in the different study area. It's like if it's the computer science, it will be like break point. If we study economics, it will be like segmentation. Also like structural breaks or regional switching or detecting disorders. And also change points can be found in a wide range of literature, including the Quantile control, economics, environment, and liquid physics. And there's a graph for change point. So suppose we have the data from Y1 to Yn. Now suppose we have a change point exists at tau, then Y1 to Y tau will differ from the Y tau plus 1 until the Yn in some way. And there are mainly 3 types of change. So first is a change in mean. You can see the first segment, the mean for this first segment is like 1, and the mean for the second segment is 0, and there is 2, and the last segment is like 0.5. So the first type of change point is change in mean, and the second type of change point is change like variance. So you can see the first segment is like the first 100 point. There is a small variance. Now for the second segment, maybe like 100 to 215. The second segment will have a larger difference compared to the first segment. And the third part, like some smaller, but larger than the first segment. The last segment will have the largest variance. So the second type of change point is changing variance. And the last type is like changing the trend. You can see in the first segment here, like we'll have an increase slope, but then like decrease slope, like then also increase, and the last segment will have the constant trend. So the slope is constant. So there are mainly 3 types of change: changing mean, changing variance, and changing trend. And for the change point detection, there are 2 types of change point detection. So what's the change point detection? It's really referred to the process of identifying abrupt change in data set. So will the specific property of time series shift at a certain point. And this test is crucial for understanding spectral change in data and is closely associated with other problems, such as change point estimation and change point finding. So the first change point detection is online method. The second change point detection is offline method. And for the online method, it's like real time and will be like sequential processing. And the goal of online method is quickly detection of change. And application for the online method is where like real-time monitor, like the Quantile control financial trading, network splitting or fault detecting in machinery. For the offline method, actually my research will focus on the offline method. This is the batch of processing, and this is like the retrospective analysis, and will be more accurate comparing to the online method. And the application will be like the historical analysis, like the climate study, and also some mapping analysis. And
That's good.
sorry.
Yeah. So when you talk about detection, do you detect the type or define the type of a change point?
Sorry.
Do you detect the type of a change point or you define it? Like you show that there is 3 type of change point. Yeah. So
This is a change point type, but this is a change point detection method.
yeah, so you define the type first and then you detect the change point.
Yes,
Okay. Yes.
thank you.
Thank you. Sense.
So for the literature, actually the literature will mainly focus on 2 types of change point techniques. The first will be the single change point techniques. And second is multiple change point techniques. So for the single change point techniques, the first is the commutative sum test. It is the first introduced by Page and is defined like equation 1 here. So this is actually to define the mean. You can see that if I have a potential change point K, I need to calculate some the mean before this change point and also calculate the summation of this change point. And then compile this, then I identify this potential change point. And the second change point technique is like likelihood ratio test. So likelihood ratio test will have the null hypothesis that suppose there's no change point, and alternate hypothesis will suppose at most 1 change point. And you can see from the equation 2 here, this is my test statistic, and this is my ratio test. So this is the denominator is like my null hypothesis, and denominator is that if I have a potential change point K, and the first part will follow the parameter mu1 hat, and the second part will follow my mu2 hat. So this is for likelihood ratio test. So you can see from the equation 1 to actually both this single change point text will focus to detect the changing means, and will be only for the single change point detection. So however, for the multiple change point detectors, we have a binary segment. This is like introduced by Scales and Knott. So binary segmentation works by literally applying a single change point detecting organization to different subject of sequence and extending to approach to handling the multiple change points. So a change point can be defined by equation 3. You can see that if I have a potential change point tau, now I calculate the cost for the segment y1 to tau plus the cost for the segment y tau plus 1 to n and plus my penalty. If this summation cost less than the total cost from y1 to n, then we'll think that the change point improves my cost. So this is my potential change point. Now the second multiple change point technique is the wide binary segmentation. And actually, this is improve the binary segment by randomly choose the subsample. You can see from here for this example, I randomly choose the subsample S and E for 1 less equal to A less than equals to B less equal to N. Now, if I can find this, the total segment for Y S to E minus my potential change point divided the total segment to 2 target segments Y S to E, and YT tau plus 1 till E and apply my penalty. And this is bigger than 0, then I don't think there's a potential change point here. And the binary segmentation and the wide binary segmentation will be like computation expensive and will be sensitive to noise and it could be detect some false positive. So there's a weak part for the binary segmentation and the wide binary segmentation. And the last method of the multiple change point techniques is the penalized likelihood method. This is what I used for my research. So the objective function will be like equation 4. Yeah, I will calculate the cost from tau I minus 1 plus 1 until tau I, and calculate this cost function plus my penalty. So this is my objective function. Then I will find the maximum likelihood actually is to calculate the twice. This is usually do like the twice negative likelihood. So like equation 5, this is what we usually do. And solving the penalized optimization problem, this is like the computer course to as well. And we also introduce a new method for the PELT, Pruned Exact Linear Time algorithm, developed by Dr. Blake. This is like to improve our calculation cost. Yeah, but it's more efficient and more reliable. And for the motivation of my research, the first we'll consider slope change. So in the past literature studying about the time series data, the balance data, actually they will assume the same slope. You can see the picture here. They detect a different change point, but they assume the same slope. So the motivation of my research, the first one will I will change all these slopes. And the second motivation is like globe trends and seasonality. All this picture actually is about temperature and mode and D. And the top one is the average temperature. Actually, you can see that this is increase. So the monthly average temperature will follow some seasoning pattern. Yeah, more clearly from the middle part. The middle part is monthly sample means. So you can see the January, the temperature is very low. Now the February is a little higher, and on maybe the July, the temperature is highest. Then the temperature will decrease until the September. Sorry, until the winter time. So you can see from the average and temperature mean is like bell shaped, right? Now the bottom one is like the standard deviation. So you can see in the winter time, the standard deviation is larger compared to the summertime. The summer will more standard. Yeah, the winter will like change more. So the second motivation will be like I will to detect the growth trends and the seasonality. And third motivation is called autocorrelation. So in the past literature, they assume the weather temperature arrow follow the identical and independent, but actually they are not true. You can see from the picture here. It seems like that the temperature is relatively constant before the 1970s. But after 1970s, the temperature accelerates very quickly. Yeah, you can see this, the warmer is higher and higher. Is that true? Actually, no. You can see the little graph here. There's a highly autocorrelated arrows to show. So we cannot just telling from the trend here to say that there's a warming survey. No, because we don't consider the temperature arrow, they have some high autocorrelated. So my third observation will to consider the auto correlation. And the goal of my research will be like to detect changes and growth trends using regression parameter. And also identify distribution change beyond the mean and standard deviation change. I also detect some trends. So also handle the time-dependent data. The past literature only handle the identical and independent data. And also combine Quantile Autoregression with PELT for optimization penalized cost function. Also, I will to develop more efficient and reliable algorithm. So what's the Quantile regression model? The Quantile regression model has a equation 6 here. Now I have my pair of observation xi and yi. So yi is like the linear regression for the xi times beta times my error term. Now the estimation of beta will be like minimize objective function and the objective function 7 here. Now the rho tau is my check function is defined like equation 8. So u times tau minus I and times it's indicate mu less than 0. So if u less than 0, I will give weight to the tau, and then mu greater than 0, I will give the weight tau and this u times I. And if the arrow, if the arrow follow the Quantile regression model, then maximize my Quantile regression model actually is the same as to find a symmetric Laplace distribution. So next, I will introduce a symmetric Laplace distribution. The standard Laplace distribution is defined by equation 9 here, and tau times 1 tau. Tau is my Quantile, and the sigma actually is a scalar parameter, and time exponential, the negative rho tau. Rho is still my check or loose function. And the mu is my error term, divided by my scalar parameter. So if I want to maximize log likelihood, will be the same as the minimize negative log likelihood. So I have to add my equation 10 here. So for the residual, the objective will to reduce to minimize my equation 11. So if I take derivative for log likelihood function, I can get my estimate to the scalar parameter will be like the summation rho tau mu I divided in. So this is like my loose function and depends on my Quantile and based on my error term. Now for the Quantile autoregression, we'll use like starting from my classical AR1 model. So for the AR1 model, it's like equation 3 here, 13 here, sorry. Yt equals alpha 0 plus alpha 1, yt minus 1 plus my error term. Now, if for the tau's conditional Quantile function, y tau are all pairwise like alpha 0 plus alpha 1 tau times 1, yt minus 1. So this is my log value. Now, if the most of the time the noise term will not well behave, so we'll like the alpha 0 depend on tau, and we can write the equation 15 here. So I will let my coefficient and my slope depend on tau. So it means the Quantile autoregression will more capture some non-normality or hostochastic compared to some basic AR1 model, just because I introduced some tau parameter here. Now, if I define the yt equals like a vector y and a yt t minus 1, and alpha t is alpha 0 and alpha 1 tau, then I can get more compact formula here. Now, PELT. PELT is very useful to detect a change point. And PELT is introduced by Dr. Leak. It will assume that when introducing a change point into a sequence objective cost C, the sequence will reduce. So more formally, we assume there exists a constant k such that for all t less than x less than t. So from equation 7, it can be said if I have a potential point into x, Now for the segment t plus 1 until s, and also the second segment is plus 1 till t. And these two costs, the summation of these two costs and plus my penalty less than the total segment t plus 1 until the t. So it means my change point also improve my cost. So this is my potential change point is verified by equation 17. But if the equation 18 succeed, like the ft is my cost function for the t, and plus my cost function for t plus 1 until s, and plus my penalty greater than my cost function at s, it means my s by t cannot never be last change point. So for means the t will be proving because we do not improve our cost. So the previous change point t will be proving by equation 18. So that's like the algorithm and the method for the PELT. Actually, this is something. This is some video you can. Yeah, this is the visualization PELT by Pruned. Or this is video I cannot play.
You could try copying that URL you have at the bottom into.
Sorry.
You could try copying that URL you have at the bottom where you have the source HTTPS.
Yeah, can you see that at the bottom of your slide? You've got the URL for the YouTube.
Oh, okay, yeah.
Oh.
I do some change point first, but I will prove it. Some not so true change point. Sorry. That's over.
Or did you close your slides? They're on the desktop.
Okay.
Yeah, there you are.
Okay. Yeah. So my primary work will be like my objective function, as I said, I use a penalized likelihood function. I will calculate the cost for each segment, tau I minus 1 plus 1 until tau I plus my penalty. So for each segment, I will do the linear regression first. And I will use ordinary list as well in R. And also for the error-10, I'll do the quantile regression, like use the RQ in the R to find the minimize the quantile estimate function for each error-10. And then I will use my try likelihood log-like function. And for the penalty, I will use like the EIC. So we can see there's a beta 0 and beta 1. So there's 2 here. And also I have an alpha 0, alpha 1, and my ET. So all these 3 parameters will times my quantile K and also my change point. So I have 3 times K plus 1 log n parameter here. So for the first example, I generate the 100 data. So the first data will follow like the autoregression coefficient, like the positive 0.05. And second data, first will follow the negative autocorrelation, negative 0.7. And I choose quantile like 0.25, 0.5, and 0.75. So you can see that it's obviously there's a change point like 50. But I use my method. You can see the solid black line here. My change point is 49. This is 1 point missed from my two change point data. So I think my work is really good. So also the quantile equals 0.25 and quantile equals 0.75. You can see that. So this is 0.25. So the lower quantile data more sensitive to that. And when the quantile equals 0.75, so the some upper tail will more sensitive to the quantile 0.75. And in my second example, I use the annual temperature at the last boost Alabama. So this is a 100 average year temperature showing from here. And I use my method to detect there's a change point 1919 and then 1979. And also my change point is 1957 and then 1975. But for this time series data, it's not have a 3 document station change at the year 1913, 1956, and 1987. So my method successfully detect 1939 and also this is very close, 1956. But I didn't successfully detect 1978. And I have a more change point like 1990. This is because in the previous, they didn't change the slope, but my method also changed the slope. They didn't capture some temperature trend change, but my method captured the change point. You can see here. So there's a slope change in the 1990. But in the 1987 factor, there's no change point, no obvious rate temperature trend change. So I don't think there's some temperature change point here. And also this is the quantile for each segment. So in the first segment will be in the 1990. So you can see this is more stable. Now the second segment from the 1990 until the 1939, right? This is more variance compared to the first segment, and third segment is more stable. Yeah. So this is like more variance. This is like great variance for the last segment. So my future work will be like to incorporate gradient for EM step and iteration solution. I will use some model to estimate initiate growth parameter. Then we will to detect some changing point using the PELT method. Then update some micro parameter estimate on the detect change point. Also, I will to enhance the Quantile Autoregression fitting split, like use the differential method to estimate the cost function for quantile roots. Also, we'll apply the empirical likelihood approach. So we are studying this now. And the last method, I will to like to use R language, not just use C language, not just R language, to boost my computation efficiency. So that's my reference. Thank you.
Any questions?
Could you try doing this on something like a noisy exponential that doesn't have like any shifts or anything, but you know, if you were to try to do this method on a exponential, it should have like changes in the slope. But did you try seeing if like that would, if it would give you results that you would expect? I would imagine it would give you like what would it be? Something like drawing a blank on the word, but like the same a change point after like a unit 1 and then a change point after a unit half or and then a quarter or something like that. A geometric progression of change points. is what I would imagine you would get with a noisy exponential. Did you try testing something like that, or?
No, I'm not sure, yeah.
I just mentioned that because the climate change, they kind of have like, it's kind of like going up and faster, and so.
Yeah.
The idea is maybe
Yeah, I think.
how much of that might be, like, if your model may not be able to represent it, but it may have some indicators to say like, this is something else rather than just change points. Maybe it's like detecting something else at certain points.
Thank you for this question. I think that it's very helpful maybe in the future work, yeah, thank you. I didn't do that.
Other questions? All right, well, thank you guys. And next week, we have another speaker, who will be speaking on intern that he did. So I hope you guys can come to that. It's